In video 1 I told you every weighing system does one job: turn a mechanical force into an electrical signal. Today we open up that black box. By the end of this video you'll know exactly what's happening inside a load cell, why it outputs millivolts and not volts, and which load cell type you should expect to find on which application in your plant. A strain gauge is nothing more than a thin metallic foil, printed in a zigzag pattern, bonded onto a flexible metal body, usually alloy steel or stainless steel, called the load cell's spring element or elastic element. Here's the physics: when you apply force to that metal body, it deforms, not visibly, we're talking deflection measured in microns. That deformation stretches the zigzag foil pattern in one direction and compresses it in another. And when a conductor stretches, two things happen: it gets longer, and it gets thinner. Both of those increase its electrical resistance. Compress it, and resistance drops. That relationship, the ratio of resistance change to strain, is called the gauge factor, typically around 2.0 for standard foil gauges. It's a small effect. A full-scale load might only change gauge resistance by a fraction of an ohm out of a 350 ohm gauge. Too small to measure directly with any useful accuracy, which is exactly why we don't use one gauge alone. This is the part every technician needs to actually understand, not just memorize, because when you're fault-finding a load cell in the field, you're measuring bridge resistances, and if you don't understand the bridge, you're just comparing numbers you don't understand. A load cell uses 4 strain gauges wired into a Wheatstone bridge. 2 gauges are mounted so they go into tension under load, 2 are mounted so they go into compression. They're arranged in the bridge so that tension and compression gauges are on opposite arms. You excite the bridge with a stable DC voltage, commonly 10 volts, sometimes 5 or 15 depending on the cell and the instrument, applied across 2 opposite corners, called EXC plus and EXC. With no load, the bridge is balanced, and the output across the other 2 corners, SIG plus and SIG, sits at 0. Apply a load, and the tension gauges increase resistance while the compression gauges decrease it. That imbalance shows up as a small differential voltage, the signal output. The reason we use 4 gauges in this bridge arrangement instead of 1 gauge is twofold. First, it multiplies the sensitivity roughly 4 times over a single gauge. Second, and this is the practical part, it cancels out temperature effects. All 4 gauges see the same ambient temperature, so thermal expansion affects them equally and cancels out in the bridge math, leaving only the strain caused by actual load. That output is rated in millivolts per volt of excitation. You'll see it on the load cell nameplate as something like 2.0 millivolts V. At 10 volts excitation and rated capacity, that's a 20 millivolt signal. That's what your indicator or transmitter has to amplify and convert into a usable reading. Not every load cell looks the same, because the mechanical arrangement changes depending on how the force is applied. Compression load cells, these see the load pushed straight down through them, like a button. You'll find these under storage silos and hoppers, where the whole vessel sits on top of the cells. Shear beam load cells, these are the workhorses of beltway feeders and platform scales. Force is applied partway along a beam, and the cell measures shear strain rather than direct compression, which makes them accurate even with some off-center loading, important on a beltway where material distribution isn't always perfectly centered. S-type or tension canister load cells, shaped like an S. Used where the load is hanging or pulling, common on hopper scales suspended from above, and on some batching systems. Canister and single-point load cells. A single-point cell can handle both vertical load and some off-center loading without needing multiple cells, common on small platform and bench scales, less common on heavy plant equipment. For weighbridges specifically, you'll almost always find compression-type load cells, typically 4 to 8 of them under a single deck, depending on deck length, each one rated to handle a share of the total capacity plus a safety margin for dynamic truck loading. Every load cell has a nameplate, and every technician on my team knows how to read one, because it tells you what normal looks like before you ever put a meter on it. Rated capacity, the maximum load in kilograms or tons. Rated output, the MV figure we talked about. Excitation voltage, typically 10 volts DC, sometimes stated as a range like 5 to 15 volts. Input and output resistance, typically around 350 ohms for most industrial cells, sometimes 700 ohms on higher precision types. And accuracy class, often expressed per OIML or NTEP standards if the cell is used for legal for trade applications like a weighbridge. Write these numbers down for every load cell on your plant. When you're troubleshooting 6 months from now, the difference between a healthy 350 ohm bridge and a corroded one reading 280 ohms is the entire diagnosis, but only if you know what it should read. That's the load cell, a strain gauge Wheatstone bridge turning microstrain into millivolts, packaged into a mechanical body shaped for the job it does. In video 3, we move from theory into the real hardware you actually operate day to day, the beltway feeder, how it holds a mass flow set point in a closed control loop, and the mechanics that make that possible. Subscribe if this is useful, and I'll see you in the next one.